Welcome to AP Calculus. Here's our Part B homework starting at number 32 from section 5.2. First off, we're going to start off with some antiderivative work. And if you haven't seen Part A, you may want to take a look at that. If you haven't seen the lessons, you may want to take a look at those. But we are supposed to find a function f that would ultimately have the derivative 2, but we're really not supposed to find a function, we're supposed to find all. And that becomes a huge issue for us, and we better get in good habits with it right now. So antiderivatives, there's a ton of functions that could give me a derivative of 2. For instance, 2x does, but so does 2x plus 4, and so does 2x minus 7, and 2x plus square root of 3. It can be 2x anything, but I know I can kind of in my head be thinking of this as like, oh, this is 2x to the 0th, so what would give me a 0th degree derivative? It has to be a to the first, so f of x has to be this, but the derivative of this is 1x, so I have to adjust that, double it. Now that is a function, but all functions would be plus a constant. That is not a variable. We don't want to think of that as a variable. We want to think of that as any constant that can go there. Obviously, if I put x there, then we don't have the same derivative. And this isn't going to be like a y where it's dy dx when we take the derivative. It's just a constant. It's just a regular old number. Okay, so number 32, we need... I'm not taking the derivative of sine, which is cosine. I need to take the derivative of something, which is sine. Well, cosine gets me in the game, but the derivative of cosine is not sine. The derivative of cosine is negative sine, so I have to adjust for that. The derivative of cosine, negative sine, opposite of negative sine, sine of x, but not the derivative, all derivatives plus a constant. Now, please note, this is just cosine of x plus c. It's not negative cosine of x plus c. Okay, and this one, 34. First thought, maybe we want to think of this. Now, what would an exponent have to be in order for a derivative to get us to negative 1? It would have to be 0, and we have x minus 1 would be 0, and that's a troublemaker for us. We can't have 0 there, otherwise we're just dealing with 1. But how else, what other derivative rule do we have that puts things in the denominator? So my little thought bubble is ln x's derivative is 1 on x. So I could try this, ln x minus 1's derivative. And I'm going to leave room in case I need to adjust like I did on a previous problem. Like this one I had to adjust with a negative 1. But the derivative of ln x minus 1 is 1 on x minus 1 times the derivative of this, but the derivative of this is just 1. So that actually just does it for us. So that is an example of finding antiderivative or doing antidifferentiation without having any real rules to do it. You're going to get plenty of rules, and some of those we could probably just make up some rules along the way. You're going to get rules for this, but we don't have them yet. Okay, now find the function. So if I go back up to this one, if this said find the function whose derivative is 2 and it passes through the point 74, you can imagine what we could do here. We have our function would be a line y equals 2x, but then we would want to force that to pass through the point 74, so we'd have to adjust it. We could put 4 in for y, 7 in for x, and figure out what adjustment c would change this line with slope 2 so that it would hit the point 74. Okay, so here's one that we probably, this is the function, so we're not going to end up with a c at the end, but we might have one for a bit. Okay, so if I think of this function as, I'm going to put it above because I'm going to run out of room here in a hurry. If I think of this as, 1 on 4 x to the negative 3/4. So I think of it more of, I don't want to call it a polynomial. It's not with a rational exponent, but make it more polynomial-like. what would my exponent have to start with to end up, after I take the derivative, at negative 3/4? To end up with that exponent of negative 3/4, it would have to start one bigger than that, so it would have to start at 1/4. So f of x could be something times, or something, or divide by something, or some fraction times x to the 1/4. So when I take the derivative, I would get a negative 3/4 up here, 1/4 minus 3/4. I'm just adding 1 to this. Now, let's take a look. Do I have to adjust? Well, no, the derivative of x to the 1/4 is 1/4 x to the negative 3/4, or that. So we got it, but there's all of them. We don't want all of them. We want the ones that have an x value of 1 when they have a y value of negative 2. So negative 2 equals 1 to the 1/4 plus c. Well, 1 to the 1/4 is 1, subtract 1, c is negative 3. So our function f of x is x to the 1/4 minus 3. Let's take a look, see if that works for us. Well, sure it does. 1/4 x to the negative 3/4, and the derivative of c is 0. Okay, so we're just going to try to slap some more things together at you right here. So f of x could be, in order to end up with an x to the first, I'd need to start with an x to the second. Do I need to adjust? Nope, because the derivative of x to the second is 2x. If this was 3, I'd have to make an adjustment somehow. The derivative of what gives me 1? The derivative of x gives me 1. And I'm not even going to put a plus or minus in here yet. Maybe I'll stick with a minus. What derivative gives me cosine? Sine of x's derivative gives me cosine, but sine of x gives me positive cosine. So yes, I do need to adjust that. Plus c, and now I need a point at 0, 3. I need to force it through that point. So y is 3. When x is 0, well, that's convenient. I get 0 squared plus 0 minus sine of 0, whoops, not theta, what a habit, plus c, that is 3 equals, this is 0, this is 0. Sine of 0 is 0. So I end up with this function. F of x is x squared plus x minus sine of x plus 3. That plus 3 takes whatever curve this is and forces it to go through the point 0, 3. Okay, moving right along. Here is number 40. 40. Good problems here. We're going to have a number of different graphs we're going to sketch. I'm going to squeeze them or move them around in here. I'm going to start with A right here. Sketch a graph of a differentiable function. Differentiable basically means two things, besides it's a function, obviously. The differentiable part means it is a function, but it is continuous and it is smooth. There are no corner points, no cusps, no breaks. Can't lift my pen, got to move from left to right, and got to keep it smooth. So I want, and all I'm dealing with here are derivatives. I want the derivative to be greater than 0, or the slope to be greater than 0 to the left of 2, and I want the slope to be less than 0 to the right of 2. Now, I don't know where I'm at 2, so I'm just going to put it somewhere. There's 2. I mean, I can put it down here, up here, I can put it on the axis, so I'm just going to put it up here. But I want my slope to be bigger than 0 to the left of 2, so I got to be going up. I got to be going up this way. I need to be smaller than, oh, that is wrong. My slope to, I'm sorry, because I was moving left. Start that over, scratch that. I want my slope to be greater than 0 to the left of 2, so I have to be coming up to this. And then I want it to be less than 0, leaving that to the right, so I have to be going back down. Now, is it smooth? Or could it come up like a lot of functions do like this? It can't look like the dotted line because that wouldn't be differentiable at that point. We'd have a corner point or perhaps a cusp. Now, it doesn't mean that we couldn't do some other things besides that, but it's, I mean, I can come back here and move back up. It doesn't tell me about any Or could I? Once again, slow down. To the right, to the right of 2. To the right of 2, I need my slope to be negative, and that would mean at all times. So I've got to be coming down forever. And to the left of 2, my slope has to be positive. I've got to be coming down here to keep my slope positive. Okay, let's squeeze B in here. So B, probably be a really good time for you to try one. See if you can get through it without making two near mistakes as I did. Part B, to the left of 2, to the left of 2, our slope is negative. So I'm just going to put it in the same place. To the left of 2, our slope is negative. I got to be coming down to that. To the right of 2, our slope is greater than 2. I got to be going up. Slope's always greater than 2. Slope's always less than 2 coming in. Okay, I'm going to squeeze C over here, kind of random. This says when x is not 2, my slope is less than 0. When x is not 2, my slope is less than 0, which means I have to be coming down into here. Now, does that imply that the slope is 0 there? I'm gonna bite on that one and say, yeah, I think it is. So slope is less than 0. Slope is less than 0, but the slope is 0 here. And D, you could certainly make an argument that just a line going down, the slope is less than 0 when x is not 2. So perhaps they should say slope is 0 there. We're going to just assume that that's what they meant. So at 2, slope is always positive for x is not equal to 2. So the slope is always positive for x is not equal to 2. But again, I would argue that, I don't know why I put a tick mark there, I would argue that this fits D as well. Our slope is always positive when x is not equal to 2. Doesn't mean that it can't be positive when x is 2. So that's kind of back to your geometry logic days. Okay, this is still doing the same thing. We're trying to come up with a differentiable function, just a sketch of one, with these properties. It's supposed to have a local minimum value that is greater than one of its local maximum values. Once again, does that imply there's more? So I'm going to put a local minimum. I'm going to put it up high. And I'm going to make it look like a minimum. And I'm going to put a local maximum, and I'm going to put it down lower. And now I just have to stay smooth and get there. So by the time I stay smooth and get here, we see, oh yeah, there is another local maximum there. But this thing definitely, if I call this point A, point B, point A is a local minimum, B is a local maximum, but A is higher than B. All right, and this is number 45, and kind of a good one here. This is the last one I'm going to be doing, as I mentioned earlier. 51 through, I believe I mentioned earlier, 51 through 56 are from your assignment as well. But those are multiple choice, and I want you to put some thought through those, and if we need to discuss those in class, great. I don't want you just peeling that homework off of here. We should be able to eliminate some answers and reason our way through those. So we have a function. I'm going to sketch it just to make sense out of what we have here. We have this piecewise function. And it says our function is x from x equals 0 to 1. Well, that means if I put in 0, I get 0. If I put in 0.1, I get 0.1. If I put in 0.2, I get 0.2. If I put in 1, I'd almost get 1. But then it is 0 when x equals 1. So that's our entire function. That's f. That's f of x equals y. Okay. It is 0 at x equals 0. It's 0 at x equals 0. And at x equals 1. Its derivative is equal to 1 almost the entire time. Every point between those values, between here and here, its derivative is 1. So f prime, the derivative, is never 0 from here to here. It's It's never 0 between 0 and 1. And the graph of f has no tangent. There's no tangent parallel to the chord from 0, 0 to 1, 0. Explain why this does not contradict the mean value theorem. Remember, the mean value theorem would be one that would say, if I start here and go to there, now I'm leaving some of it out because that would maybe imply the answer, then somewhere along the line there's a tangent line, maybe more than once, maybe an infinite number of times, that's parallel to that secant chord. Well, let's go back and take a look at our mean value theorem and see what the problem is here. Mean value theorem for derivatives. If y equals f of x is continuous at every point between a closed interval, a, b, and we've got that, our closed interval was 0 to 1, and differentiable, we got some of that, by the way, and differentiable at every point on the interior of a to b, inside of ab. Now, inside of AB, I get it. This point is not differentiable at B, but it is differentiable inside of AB. It's all of these, we have derivatives. Then, there's at least one point C in AB at which the derivative there is equal to, this would be our secant segment slope, which is 0. But all of our derivatives are 1 equal to 0. Here's the problem. It is not continuous at every point of the closed interval. It's not continuous at 1. We have a jump. So we have a few theorems now that talk about being continuous and differentiable. And this one is not continuous there. So therefore, this does not contradict the mean value theorem. The mean value theorem, let's say we just finished here, would say somewhere along the line here the slope has to be 1. Somewhere along, if this is a slope of 0.8, somewhere along here the slope has to be 0.8. Okay, hope that's helpful. I think we should be in pretty good shape in this section. Some of the more challenging problems in this section, in my opinion, maybe some of the antiderivative work, but probably also some of the A problems that were a lot like 5.1, which we spent quite a few days on. So good luck going forward, and come in and ask questions if you need to.